All right. Hello, everybody. Thank you for joining the SayoStudio Podcast, where we talk about science and how best to communicate it with visuals. Today, we are so excited to talk to Trond Andersen, a Google quantum research scientist. We'll double check that I got that correct in just a moment. But we've gotten to work with Trond on several illustrations to represent the science that he is working on to advance quantum computing. And not only is he a brilliant scientist, he's incredibly kind and patient as we try to figure out how best to represent quantum, and always gives great, thoughtful feedback. So thank you, Tron, so much for being with us today.
Yeah, thanks for having me.
Yeah.
So we're really excited to jump in. To start, I have just some basic questions. Most of my questions will be basic because I think my grasp on quantum physics is very tender.
That sounds very
But yeah, so I guess my first question is, how do you define yourself? Mainly, I feel like we can have many definitions, but do you define yourself as a mathematician, a physicist, a computer scientist?
It's a good question. I definitely define myself as a physicist, but it's a very good question because we definitely do. I mean, a big part of the job is doing a lot of math puzzles, and we code a lot. I'm definitely a physicist by training, and that's the main focus of my work. But I would say that I mean, I think it was just 2 days ago I ended up spending 3 hours just sitting with a piece of paper and solving math equations, and I definitely code every day. So yeah. So in that sense, we
Cool.
practice a little bit of both, I guess.
Thank
That's-
you.
Yeah.
That's one thing that it's hard for me to I'm used to more the biology bench science, so it's hard for me sometimes to wrap my head around the daily work that you do. So that's really helpful.
Yeah, and I can, I
Um,
guess, with the daily stuff, I mean, it's really a very varied job, and I think that makes it really, really fun. I'm during my PhD, I was mainly an experimentalist, although I did a decent amount of theory work then too. I would say that when you work in quantum computing, this combination is even more natural, because at least once the quantum computer is sort of working and you can run experiments on it, you have a quite fast feedback between having theory ideas and getting experimental data, and then going back to the theory again and trying to see, was your theory correct? Should we change our hypothesis here? And then you end up switching back and forth between the experimental work, developing new calibration techniques, actually running the experiment, analyzing the data, and so on, and just doing pure theoretical thinking. And for me, that's
Wow.
kind of that's sort of the dream job,
Yeah.
because both of them are really, really fun. Yeah.
That's fascinating.
The best of both worlds, definitely.
And I should say, I mean,
Yeah.
when I was younger, I always imagined that I would be more of a theorist. I was always very interested in math when I grew up, and when I started learning physics, I thought the theory was the most fun. But then I would say the experiment has something very, very cool to it that you get to sort of. I mean, part of the reason why I want to be a research scientist is that you have this sort of really cool moment where you're the first one ever in history to see something. I think that's a really cool feeling, right? And that, I think, is something. Well, maybe a theorist would tell you that they get the same when they write an equation that no one has written before, which is fair. But there is really something, I think, to seeing something in nature, be it on the quantum computer or in a more typical sort of condensed matter experiment, which is more what I did during my PhD. But seeing something and knowing that this is something that no one was aware of, no one has ever seen. You can go 1,000 years back, no one saw it.
That's
is a really,
amazing.
really thrilling experience that I think makes the experimental component extremely cool as well.
So can I ask a follow-up question about that? So I started out my science illustration, science communication career with an internship at the Stanford Linear Accelerator.
Okay.
And so it felt like back then, okay, I'm just going to do it. I'm going to say how long ago that was, like 20 years ago. You didn't have that immediate feedback to be able to test theoretical ideas. Like there was a ton of resources involved to get time on things like linear accelerators or use telescopes to look out into space to test physics theories. Is that one thing that quantum has really changed, is being able to quickly test these theories? Is that changed, or am I
No,
misunderstanding?
I think that's exactly right. At least to me, I can't immediately think of any other platform or any type of job like this where it would be a faster turnaround. I mean, during my PhD, we had, I would say, 5% of our ideas we actually went ahead with because we knew that it's going to take 3 months at least to develop the experiment, to develop even just fabricating the samples for the experiment. So you had to be really, really careful to pick the best ideas and not sink too much time into something that turned out to not be a good idea. But here, in the way, I mean, because this quantum computer is already, the chip is there, it's working very well. We have already very good calibration systems and so on. You can really have an idea in the morning, have it tested by 3 p.m.
Yeah.
and have sort of nice plots of it by the time you go to bed. And that's a very unique research situation, I would say.
Yeah, that's amazing.
Wow.
Yeah, it's kind
Wow.
of I would say, the dream for a physicist, especially if you're a bit impatient, which I am. So
That makes me think about, like, the added pressure of, like, the innovations, like, your ideas, and I'm curious, like, where do you find, I don't know, like, pushing yourself to, like, think outside the box, and if you're looking for inspiration or kind of that, if you can test these things so quickly now, you know.
yeah, it's a very good question. I would say it's a combination of many things. I mean, of course, we have a lot of discussions in the team where we just brainstorm and try to think of what would be
Okay.
the most exciting physics to see. Then, of course, you travel to conferences and talk to people and listen to presentations and hear about new interesting ideas that people would like to see realized in an actual experiment. And then, of course, a lot of it is you do an experiment, you see something in the experiment, and then oftentimes I find that now that we have a dog, that going on a 5-minute walk with a dog, then I very often during that walk, I think about the data and then I realize, wow, I should change the experiment this way instead. So very often you start out with some form of the experiment, but then you realize that this is a much more interesting way to do it just based on the data that comes in. Yeah, so there's several processes I would say that very often ends up with being a good experiment. And then, yeah, I guess also there's another example of where we had theorists, in this case from academia. We collaborate a lot with people in academia. Uh,
Mhm.
but for instance, we had this one paper where we realized this braiding of non-abelian anyons for the very first time. And in that case, that was a problem that's been around for decades. People have been really trying to see these for a super long time. So you could say, in that sense, that idea in itself had been there for a very long time. But that
Mhm.
some very, very smart physicists at Cornell, one of them, Yuri Lansky, now works with us, had an idea for how that could be realized on a quantum computer. And then we worked together with him to make the first realization of this braiding, which is really cool. I mean, the fact that something that people have been trying to see for decades, now you can actually see because you have a quantum computer. Yeah, the fact that you can actually use the quantum computers to do these types of experiments and realize new physics, I think is really, really cool. And is maybe not how most people think about quantum computers. And I'm not sure if it's obvious to everyone that actually already they are a fantastic platform for just realizing super cool physical phenomena. Of course, to someone who's not in physics, we think about computers maybe not as an experimental platform for doing physics experiments, but that's really a lot of what we do.
So
Cool.
that helps answer my question of like what is so exciting about quantum computing. There's so much hype about it in the media. And I don't think I'd actually ever thought about it just furthering physics understanding and research and experimental possibilities. I mean, I think everybody talks about it more like with banking password,
All right, exactly. Yeah.
security and that sort of thing. So,
No, and of course,
um,
those are important applications that we are working towards as well. But I would say at this kind of early
mhm.
stage, a lot of what we see is these really cool physics experiments.
Yeah.
And you can really think of
And
it
that's
as, I
all.
mean, during my PhD, we were studying these the 2D materials, atomically thin, very, very cool materials that have
Mhm.
all this cool physics, and there's a lot of predictions for the physics that you want to see there. But the really difficult part is having enough control over the quantum physics that happens inside of that material to realize
Mhm.
exactly the thing that some theorists had a great idea of. Because you don't have perfect control of every atom, of course, and there can be dirt on it and all these things. And in many ways, you can think of a quantum chip as being a perfectly controlled quantum system. So it's sort of an engineered system where we can control the energy of every qubit, which you can compare a little bit to controlling the energy of every atom in some material. And so that gives you this whole new level of control and ability to do things that people have proposed, because now you can actually control it to be exactly what the theorists thought about, and not just try your best at it. Yeah. So in a way, it is an engineered, humanly controlled material that we have here. I think you can see.
Yeah. That is so helpful because I think even though we've gotten to work with you for a long time, I still forget that this isn't all just numbers whizzing past. Like, there's actually qubits where you're running these experiments through. And can I have a photo, of the computer. Can I show that?
Yeah.
Just
Cool.
see if it'll well, and so just to let's see. Can it show up? I think it can.
Yeah. Beautiful.
So I think one thing that is interesting about this is, like, this is mostly all just to cool it. Is that right?
That's
And the
right.
actual
That's right. So the chip itself is a lot smaller than that, where the actual qubits sit.
and is that like, where is the chip itself?
Yeah, at the bottom.
Or are we giving secrets away? I don't think we're giving secrets away.
I assume this picture is public. But yeah, so all these wires go to a chip that's towards the bottom there.
Yeah.
Oh.
Yeah, this was from, when we got to go visit the site in
All
Santa
right, because you
Barbara.
guys visited. Yeah.
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 Yeah. So, yeah, it's so fascinating, the interplay between the hands-on engineers who are building all of this, and like you said, you get to work closely together and actually do a lot of it in addition to actually running the experiments to further physics understanding and knowledge.
And I should say, I mean, those engineers doing that and all the people working on that is the reason why we have this incredibly fast feedback time of new ideas. I mean, this doesn't happen magically, but it is because someone has already developed things and are currently working to sort of keep these things stable and doing a fantastic job with that.
Mhm. Wow.
And
So
how cold are those qubits? Close to absolute zero, right?
Close to absolute zeros, it's tenths of millikelvin. Let me think of how to. So a Kelvin is 1/200. Well, we can say 1/300 of the temperature that we have in a normal room. And then you still have to go down to sort of the percents of that again. So it's ridiculously cold. This is kind of, I mean, we say that liquid nitrogen seems very, very cold. This is way liquid nitrogen, for instance. Yeah. And it's only, you really
I
have to go
think
down there for the quantum computer to work properly.
And I think that could be considered like the coldest space on Earth or something
Yeah,
like
it's a good
that.
question, actually. Yeah, no, people use other techniques for cooling, just like atoms and so on. I think they can go even lower.
Okay.
But yeah, here I'm actually a little bit iffy on the details of exactly what the quantities or the magnitudes are. But yeah,
so
definitely
can
extremely cold.
yeah, I was going to take us to the very basics of some quantum questions. So my understanding of what is so powerful about quantum computing is that a qubit, so like the base particle, and actually now I realized, can you give us a description of what a qubit is for our listeners?
Yes, so a qubit can be many things.
I know that's a big question.
So the main thing is that we want something that can be in two particular states. But then, unlike a normal bit in a classical computer, we want this thing to be in two different states at the same time. So we want some very clean system. Typically, we have to cool it down to achieve this. That's not interacting too much with the environment, so that we can have super clean, so-called superpositions, which just means that they're this in 0 and 1 at the same time. But this can be many things. So it can be an electron in an atom being in two different orbitals of the atom, for instance. In our case, it's a circuit where the circuit is in two different states. It's an oscillating circuit where it's in two different states at the same time. It can be a photon that's in two different states at the same time. So really and I think this is one of the really cool things about quantum computing at this stage is that we don't know for sure even what the qubit is going to look like in the final quantum computer, because there are still many different ideas for making them, and I think that's actually a very exciting stage to be at, where even that is sort of still something that we will see. Of course, we're very optimistic about the superconducting qubits that we use at Google.
And so I assume that even if one area that a group is using to study doesn't pan out, it's kind of not the winner, in which qubit will be the supreme future quantum computing core bit, that you're still learning a ton of things that can be applied regardless of the
Yeah,
system?
exactly.
Is that
Well, for sure.
okay?
And I mean, it's super interesting to look at the other platforms as well, and seeing
Mhm.
how different specs of the qubits compare. One qubit can be very easy to control, but maybe it lasts for a very short amount of time. Maybe another
Mm.
one lasts for a very long time, but it's really hard to actually control it properly. Oftentimes, it's
Mhm.
hard to get two qubits to interact with each other, which is a crucial part because that's the logical operations. So that
Mhm.
also varies from platform to platform. How easy is it to achieve that? Yeah. So it's a very fun landscape, I would say, of different efforts.
Yeah. I
Mhm.
um yeah, it's fascinating, and I guess I wish that I fully understand it. I always feel like I'm just about to get it, and then I just kind of get the surface. Do you
I have to say, I'm
think
always very impressed when we have meetings with you guys about the art. I'm always very impressed by how much of the quantum you guys know.
well,
And me, it's
that's
not
good to
easy
hear.
stuff. I guess it was Niels Bohr who said that if you truly think you understand it, then you
Yeah.
don't actually understand it. So I think
That's encouraging. I guess I'm curious, is it really possible to understand quantum if you don't have the high level math? Like, is that a necessary skill set to really
very
dig
interesting
in?
question. I like the question a lot because I mean, of course, I think it's definitely a benefit to have some of the math tools. I definitely don't think it's necessary for at least understanding the main concepts, and maybe in many cases, actually understanding it without referring too much to the math is when you almost have the best intuition for it. I notice
Mhm.
many times when I learn about something new in quantum physics, I can just read the math, and it's nice because it gives me sort of a very concise explanation of what someone's trying to say.
Mhm.
Um, but it's not really until I feel like I have an understanding beyond the math that I really feel like I understand it. So if someone says, clearly it's obvious, just look at the math here, then I would often say that, sure, I totally agree with the math, but I don't feel like I have the correct deep understanding of it until I sort of go beyond that. So I think actually in many cases, learning quantum physics without just looking at the math, but more kind of getting intuitions for things, I think is oftentimes more powerful. I would say.
Well, this
And
gives me hope. I'll keep working on it then.
I'm not just happy there.
and so is that, if I'm understanding correctly, that would be kind of like the experimental side, which is that hard math, versus then the larger theory side, which you talked about in the beginning of you kind of marrying both and it being this ideal mixture for you?
I would say definitely on both sides, I do a lot of math,
Mhm.
but also on both sides, I try as much as I can to ensure that I also have an intuitive understanding of what I do. Um,
Okay. Okay.
So, for instance, I mean, in some of these experiments that we're doing now, we're studying qubits that simulate magnetic spins, sort of magnets that interact with each other. And many times I can write up the math for it and explain what should happen. But it's far more helpful if you really think about what are these spins doing relative to each other and how is one pulling on the other and so on. That's really what I think when you're able to make the best predictions and come up with the best ideas, because then you have an intuition for, wow, I can really think about this one moving like this and it turns this one over like that and so on. And that's not based on math at all. That's just based on knowing sort of how magnets work.
So, I've been waiting to ask this question. So, sorry to take us in another direction, but one of the really basic things about quantum that I just can't quite wrap my head around is, so So a typical bit is 0 or 1. It's basically black or white, right? Like in our traditional computing systems. And so quantum is exciting because it has all the different states. Like it's like a full rainbow, if you will, like of all the is that right? And so what I get confused about is when you actually measure it, then it reverts back to 0 or 1, right? It's like
So first
a
of all, I
binary
should say
system
that
once you measure it.
I really like your point about rainbow because I think a lot of people would say that the qubit is gray.
Uh-huh.
And we often, yeah, I see this very often. And then you kind of lose the beauty of quantum because it's not just that. I mean, if I just said, oh, I have something that can be 50% of one and 50% of the other, so it's gray
Mhm.
instead of black or white, um, then it really wouldn't have most of the power that a qubit has. Because really the power that it has is that you have also we call it a phase, which describes the relative relation of the 0 and the 1 inside of that qubit. And that phase can be, again, we don't have to do, we don't really need math. It can be anywhere around the circle. So really all you need to think about is it's some number around the circle. And the magic of this is that around that circle, there's also some negative numbers. And this is important because that means that I can
Uh-huh.
add two states together and I can get a smaller number. And this is the interference part. So if we thought about just probabilities, just a number from 0 to 1, just grayscale, then you would imagine that you add 20% and 20% and you get 40%. But here, because we allow ourselves to have something more than just a simple number like that, but something around the circle, then you can have, for instance, negative numbers, and negative and positive together can add to 0. And this is the interference part. And this is really where we get the cool effects of quantum physics. It's not just adding 20 and 20 and getting 40, but it's that sometimes the interference pattern gives you 0, other times it gives you a positive, say, 100%. And this all comes from that color scale instead of just having a gray scale. So I really, yeah, I think it's a cool.
That's a great description. Thank you.
And I would also say it relates very much to, I'm sure we're going to talk later more about the sort of design of, or the arts of things. But I think very often when we try to come up with good analogies for quantum,
Mhm.
sometimes you hurt yourself by doing that because you simplify it too much and you lose kind of the magic of it. We had
Mhm.
this presentation for this EU Council last fall. We tried to come up with good analogies and simplifying things more and more. And I noticed many times that, wow, we're simplifying too much here, so that now people will not appreciate how you're supposed to think that it's crazy. I mean, it shouldn't sound like it's easy. If it sounds like it's easy, then you really haven't gotten the message. It should sound completely absurd. There really is. I mean, it is so counterintuitive. It shouldn't sound like something intuitive. And that's why one has to be careful and use color scale, for instance, instead of grayscale. Yeah. Sorry, there was another question about yeah, what was at the end again?
Well, I get hung up on the measurement part
Yeah,
because
yeah,
when you
sorry.
measure, it reverts back to binary, doesn't it? That's where I get confused how we can use this full spectrum.
That's exactly right. And it's a really, really good question that I think many people often skip over. So let me try to think of a good way to think about this. Yeah, so oftentimes one way that one can sort of describe the power of a quantum computer, it's a bit of a simplified way, but I think it's still helpful, is to think that, okay, in a classical computer, if I try to find the fastest way to a restaurant, then the classical computer sort of tests one way at a time. So it tests
Mhm.
first, I'll go left, and then I'll take a right, and then left and take right, and then I test another path. The quantum
Mhm.
computer can be both 0 and 1, both left and right at the same time. So you can sort of explore many of these paths. So that's really the big power. But then, as you said, I'm exploring now many, many paths. But at the end, when I measure, I can really only measure sort of one of the states.
Yeah.
And this is why a quantum computer doesn't immediately just get infinite power, because you need a very smart algorithm that actually makes sure that somehow the probability all goes back to the fastest direction, the fastest route, I mean,
Yeah.
so that I actually get to the best solution in the end. So I have this, I guess another way to think about it is you can think of all these probabilities, this crazy distribution as some kind of like wave pattern that we quantum physicists try to guide so that it's doing something cool. But at the very end, I need I need the wave pattern to sort of get focused at the right solution because, like you said, I can only measure one of them in the end. And so it's not enough to just be able to explore all possibilities. You need to make a very, very smart quantum algorithm that somehow focuses into the right one at the very end of it. And that's why making quantum algorithms is a big field and a very, very interesting field. Yeah.
I'm going to have to sit with that and think about it, but thank
Okay,
you.
but to give a sort of maybe an even quicker or maybe a more general point, the measurement only happens at the end. So you're not
Okay.
measuring during the circuits, of course. If you did that, then indeed you would sort of break the quantumness every time you were looking. There are certain techniques you can do this, but no. So that would kind of break it. So the important thing is that you explore all possibilities during the simulation or during the computation, and you take advantage of this crazy superposition power. But then at the very, very end, like you said, you need to do a measurement.
Yeah.
And that's when it actually collapses.
That's a really helpful explanation for me. Kind of like just in my head imagining, the power is when no one's watching.
Exactly.
And then, but you have to get an observation out of it,
Exactly.
or then there's no power at all. So
Exactly. Yes. And
that's
actually,
really,
and then
really
I think
helpful.
very, very nice way one thing that comes out of this that I think is very neat consequence is that if someone was watching, that would ruin your quantum computation, right? Most likely no one's going to come into your lab and start looking, but you can think of depends a bit on the system, but say there are some electrons in your chip that shouldn't be there and they are interacting with your qubits, then in a way, these electrons are sort of taking a look, right? So someone's actually
Oh.
and that ruins the quantumness, and that is exactly what we call decoherence. The big problem in quantum computers is decoherence because someone's looking. The electron is taking a
Oh.
look, and like you pointed out, that breaks the whole point of the quantum computer.
Yay, I learned something new. That's wonderful.
Wow.
That's
That's
a
So
what
not
decoherence is.
so anything that kind of it functions as like a memory or storing or is breaking it.
anything that's sort of affected by the state of the quantum computer, which is
Mhm.
kind of what looking at it is, right? I mean, it's if what you see changes your opinion of it, kind of. And so if an electron is sensitive to whether a qubit was up or is this 1 or 0, then that would count as looking, and that would ruin the coherence of the quantum computer.
I want to show some of the drawings, I don't know. I don't love that term. Why do I not love that term? Illustrations, visuals that we've created with you and get you to kind of walk through the concepts that they're showing us.
Yeah, sounds great.
But before I do that, I have one more tangent that might lead us astray. So
Good.
thinking about the algorithms that are really, it sounds like a lot of the work right now of trying to kind of guide the computations. Is that a good way of saying it? Um, I've never quite understood how the AI part of Google Quantum AI comes in.
Mhm.
And I've always assumed that all of this work is going to support AI, but is AI also helping with these algorithms? And I know this could be like an entirely different discussion. Is there everybody's worried about like how AI will impact them? Is it a tool that you're already using? Is it something that is taking away some of the potential work of this for good, better or worse?
Yeah, very good question. I think it goes both ways. Quantum can help AI. I mean, we know that in AI computations take a lot of power. So being able to sort of speed up those would be very nice. It also goes the other way around, where we can already start using AI to simplify some of the tasks that we're currently doing. Um, there's an example, but I'm trying to think how much background information I have to give this example. But there are, for instance, in error correction, which is this task of finding out which errors are happening in the quantum computer. People have, for instance, used AI as a way to learn what kind of errors are happening and detecting errors. So that's sort of the other direction where the AI is helping the quantum computer instead of that way. Um,
Mhm.
yeah, so I think both directions are very, very exciting, and it's going to be, I think, super cool to see where it goes. Yeah.
Thank you. Okay, we're already getting late and we still have other questions. So I'm going to share some art. For those of you that are listening, that we have this video form on YouTube as well if you want to check that out to see some of the art, but we hope it'll be a good discussion even if you're not able to see. So let me just share screen. So I wanted to start with one that you mentioned earlier, the non-abelian braiding piece. And so this is, let's see, this is a piece that Claire did, and I have to share that it was based on artwork from another artist that we helped clarify the visual vision of. So, Trond, would you mind walking us through what the braiding represents and why it's exciting?
Yes, I think I'll try to first give just a little bit of background of the work. I think actually it's quite intuitive and really and it's really cool. I want to say. Um, so that what we did here was we realized this completely new behavior that no other particle has ever shown before. This behavior is that if you take two particles and you swap them like this and then back again, you basically just swap them back and forth. Then there's for all particles that have been seen until we did this work, doing that does not change anything. It's almost like a fundamental law that for those other particles that we're used to, it cannot change anything. There's no way of telling. So if I told you to close your eyes and I swapped and swapped back again, there's no way of telling. But
And
then, oh, sorry, go ahead.
that's assuming like these particles are identical,
Exactly,
right?
exactly. Yeah,
Okay.
that's exactly right. So you can think of it as you take two glasses of water, you swap them back and forth, and they're still two glasses of water. But then there is a prediction that there's this crazy particle, non-abelian anions, named after Norwegian physicist Abel, and predicted initially by a Norwegian physicist as well. I'm pointing this out because I'm Norwegian. That there should be some very strange particle, some magical particle out there, where you swap the two particles. Again, we can think about the glasses of water, and then when they get back again, they're actually filled with wine. So somehow swapping them just back and forth changes them. And that's again something that no one had ever seen before, and we were able to see for the very first time by using a quantum computer. So kind of creating these objects, quantum objects on our quantum computer, bringing them around each other, and suddenly we see that they're different. And so we did that for two and three of them, but one could imagine going even further and starting to use this for actually making a quantum computation, where each swap of these particles is like doing an operation to the quantum state. So instead of doing the operations like logical or like gates that we do normally, here instead these operations would be represented by swapping positions of these non-abelian anions. And it turns out that if one does this, this could be a more protected way of doing quantum computing. That's sort of the idea. That's not what we didn't go all the way there, but that's kind of the promise. And so what we wanted to show for this art is this idea that you can take many of these and then you can swap them 2 by 2, which really forms this braiding pattern. And that's exactly the pattern that we saw here. And what kind of braid you make defines what kind of computation you're doing. And I think this is an example of one of the artworks that we've done that's more on the sort of abstract side. And I think sometimes that's really cool instead of trying to explain kind of everything with 2 glasses of water being swapped and turning into wine and these things. I think sometimes it's very nice to kind of show the more abstract idea of it and making something that's really, in my opinion, really cool art out of it. I think for certain other ones, we've sort of gone even more in the more explicit direction of getting into the specifics of what exactly the work does. I think this one was
Yeah.
very fun.
Thank you. Yeah, I think it's fun to go back and forth between the two, to sometimes just kind of enjoy the beautiful abstract art and patterns that you can make from these ideas.
Yeah, totally.
And then to kind of show one in a different way. This is one that we worked on a lot, was the KZ analog. I wanted to share that one.
Yes.
So let's see if I open that one up.
And this one is
And then
really
we're
fun.
already at 40 minutes, so I think we can jump out. But so I was going to start by just showing all of the different versions, as I think it's interesting, hopefully for people just to see how many different variations we go through. So Trond, you and I work through all of these different ideas. So we don't have to go through all of them, but I just wanted to share that. And then we can jump into kind of what the final was. And if you wanted to,
And this one
this
I
one
thought,
is,
sorry, go ahead.
oh no, you go. Go ahead.
This one I thought was a really, really fun one. And this is a very good example of where I kind of propose something that I'm not even sure is possible to draw, and I can't really picture it in my head. And then you guys come back after a week and you have something that's infinitely better than anything I could have ever imagined. So this one was, I remember when I first proposed something with an analog digital clock, I really was not sure how it would end up looking. But then it turned out so cool. But yeah, so the point here is that we made a quantum computer that works in both analog mode and in digital mode. So in one, we just have the continuous dynamics, sort of like in the real world. So we're just mimicking the dynamics of the real world. While in the other one, we use discrete operations, more like in a normal computer. So that's the digital part. And we wanted to show that we're here combining them. We're hybridizing these two techniques because that was really the main selling point of this work. And so, as you can see here, we have a clock that's half digital and half analog. But then it also has all these like cool pieces that show the quantumness of it. So I think this what do you call it, in the hand or arm of the clock?
Mm-hmm.
That's in this
Yes.
superposition. That's really sort of showing the quantumness of it. And also this ball around it, which is this is the block sphere. So it shows the different states that a qubit can be in. This comes a little bit back to this rainbow and this number from 0 to 360 degrees around the circle. That's really what's kind of shown on the equator of this sphere. So yeah, this one has really all the good quantum symbolism, but then also a more, I would say, kind of concrete description of what the work is, in that it really shows this analog digital part very explicitly as well.
And is that a direction that there's promise in using quantum with a lot of the technologies that are currently in use?
Yeah, so this is
In
a
the future?
direction that we're very excited about. It sort of
Mhm.
gets the best of both worlds. In analog, the big advantage is that the dynamics, they move very quickly. So you can very quickly get to the interesting quantum states before an electron or something looks at your quantum state and ruins it, as we talked about earlier. So before noise effects ruins the quantum computation, you can get to these very interesting, highly entangled states. So that's sort of a big benefit of analog. But then the slight limitation of analog is that it's not as flexible. While digital quantum computing is very, very flexible. You can use different combination of digital gates to do pretty much anything you want. And so if you then combine those together, you get both the flexibility of digital, but also the fast evolution to interesting quantum states with the analog. And I think we saw both in this work, and we're also seeing now in current work, that we're getting a lot of very, very nice advantages from combining those two together. So if you think
Right.
about it if you think about it from the perspective of being able to use a quantum computer to, say, make discoveries of some new physics, which is one thing I'm very excited about, then you can think of it as the digital part gives you the flexibility to pick the interesting physics question that you want to study. So you want a lot of flexibility, so you can really pick the best physics question. And the analog part allows you to evolve to the most interesting part of that physics question, so that you can really see kind of the interesting physics that arises in that setting.
That is a great description. It's fun to think about all the possibilities that provides. And one last question about the symbology in this. So in the background, I'll go back to the animated version. Oh, it doesn't want to play. Okay. No. Oh yeah, here. Let's see. Will you play? I think my internet must be slowing down. It doesn't want to play. But in the background, we have this what we call gates in the background. Again, we're kind of running out of time, but I just wanted to bring that up.
Yeah, sorry, there's so many layers of things there. I didn't even
Yeah.
cover all of it. Yeah, so in the background, it shows the quantum circuits. So this one is sort of switching from digital to analog and digital to analog. So the digital one is where we have many small circles and squares. So those are operations working on just a single or two qubits at a time. So when it's a box, it's a single qubit. When it's two connected circles, it's two qubits. And that's how we usually do the digital part. But then when it moves to the big boxes, which is thus, for instance, now you can see there's a big box in the background there. That's an operation where many of the qubits interact with each other at the same time. So that's more how the normal world works, where if you have 10 electrons, they all interact with each other at the same time. They don't talk to each other in sort of a pairwise way. So this is the analog part that kind of mimics this more, if you want, sort of real life version of interactions between the qubits.
Thank you. Okay, Claire, what do you think? Can I ask one more picture, or should we go to some of our wrap up?
Oh, let's do one more.
Okay, so one more. So this is kind of a good. I wanted to look at the cooling one that we worked on together,
But yeah,
and part of that is to lead us into the question of kind of what are the big hurdles. And my impression from working with you all, excuse me, is that one of the big hurdles is dealing with noise and in a system, which so if you could speak to that a bit and kind of what you're excited to work on and where we're going to get us to an actual usable quantum computer, although it sounds like from what you've said it is in use in many ways, but more broadly.
that's a great point. Yeah, so in this work, I think this picture is so cool. The task here was to find out a way to cool down a quantum system. And we can think about that very similarly to sort of in real life, try to make something a colder state. What we did here was that we connected it to these additional qubits. Those are the red ones, which are set up to operate in a way where they remove heat from the systems. And then we do this resets technique of them, which allows us to sort of continuously remove more and more heat in order to make and the animation is very cool. And in order to make the quantum system itself, which is the darker ones, the non-red ones, as cold as possible. So yeah, so here you can see how there's sort of freezing as we're taking heat out of the system. And then to your other question, definitely noise is one of the main problems in quantum computing. As we've talked about several times now, that's kind of the thing that effectively takes a look at your quantum state and causes it to not have these advantages of being quantum anymore. It doesn't have a nice superposition of 0 and 1 in the same way that we want. There are several things that can be done here. One thing, since we talked about it, in analog, we have the dynamics be even faster. So that allows us to be less affected by the noise. Even with the same noise amount, you can get to the interesting quantum states with less accumulation of those effects because you got there fast. And then, of course, there's a lot of work that's being done on the hardware side to just have less and less noise in the system. But then really the key effort, which is something that our team works very hard on, is developing what's called quantum error correction, which is a super clever protocol for making the quantum system tolerant to these kind of errors. And really the key idea is to use more than a single qubit to encode one effective qubit. So by having many qubits do the encoding, one can make it more robust. And if you want to think about that sort of in simplest way, which is for a classical computer, so it's not exactly the same, but you could imagine that if there was some chance that your ones turn into zeros and the other way around, then one way you could encode the one is you could use 100 ones, and then it sort of find that 3 of them flip to 0, because you would still be able to see that there's 97 ones and you know that it's still a 1. So that's how one could do it in a classical computer. In a quantum computer, it turns out it's way trickier. And it's very important that the physical qubits, the actual qubits, work very well. If they don't work well, then you have this effect where you have too many cooks in the kitchen, chefs in the kitchen. So then you don't benefit from having many qubits anymore. But so the really nice thing that we've seen in Google is that we've been able to make the qubits so good that you're actually benefiting from having many. So we see that by actually putting more and more of the qubits together, we can make one effective qubit, which is encoded by all of these physical qubits, that performs better by having many.
And that's one of the reasons why it's so important to have more qubits in your system.
Yeah, that's one of the important reasons. Absolutely, yes.
Mhm.
And so that's sort of the long term goal is developing this quantum error correction so that you're no longer sensitive in the same way to noise. But then, as you pointed out, Nicole, even without that, we can already start using our noisier qubits to already study very interesting physics. So that's kind of what we're doing at this stage.
I love learning and hearing about how much work is going in from your group at Google, not only to advancing computing, but just basic research. I think that's really
Yeah,
interesting and
yeah, no, totally, I completely agree.
encouraging when there's a lot of places where there's less and less support for that basic research. So that's incredible.
Yeah, yeah, no, and I definitely find in Google that there's a very sort of, in a way, academic mindset in this way that people are very open to new ideas and exploring many different directions as well, which makes it, I think that's a really great feature of our team.
So I think that you have another uh, obligation in about 5 minutes, so we should wrap up. But Claire, did you have one kind of ending question that you? Okay.
Yeah, I do. I'm sad we didn't get to dive more into kind of your origin story, Trond, if you will. Um, and
I
this
think we see
question
some
kind of
Norwegian stuff there, at least. So
yeah, you did. But yeah, so this question kind of lends itself to that. So I just love to ask if you could tell your 9-year-old self one thing with everything you've experienced and lived up until today, what would that be? What piece of advice would you give yourself?
oh, that's interesting. Piece of advice. The problem with a piece of advice, it sounds a little bit like I want to do something different. There's not much I want to. I mean, I really, yeah, yeah. I think the main advice would be, I guess it's better to say something I would say to my kids in a way. I feel, because otherwise it sounds like I'm just sort of trying to change something. But yeah, I would say just being super curious and doing the work that one finds sort of fun more than just sort of trying to work hard on. I think really it goes well when you work on something that you're really passionate about, and just trying to solve fun math puzzles because it's fun, rather than just doing as many math problems that you're sort of that you have to do in a book. Kind of is a one thing that's always worked really well for me. Um, and I think a bit in the same way now. Of course, that's maybe more to a 9-year-old, but even now, sort of following the kind of projects that you find really interesting and doing that. It sounds maybe a bit cliched, but yeah, I would say that has worked very well for me, at least.
That's amazing. I think that's really inspiring, for, uh, any young person, but especially any young person who loves math and that you are in this place where you get to do those things that are fun for you, um, in a professional setting. So, yeah, I think that's really inspiring.
Yeah, and I think that a lot of people who do trend toward math and computing who are really good at it feel a lot of pressure to kind of guess what is gonna be the next big trend that'll be successful, and to a large degree, you can't predict that, so the best advice is to really find something that you are fascinated by and love and want to work on, and you'll find.
Exactly, exactly.
Yeah.
And I should say, I really in Norway, I would say the school system is maybe a little bit different in that there's maybe a little bit less pressure to start to think about which college are you going to go to very early and these kind of things. I really enjoyed that it was quite, I mean, open, where you don't get very serious about thinking about those things until right before you're going to university, and before that you're mainly working to try to learn as much as you can. And I think that, or at least I really enjoyed that, and I think that only benefited my later work in math and physics. No,
Yeah, I wish we could all get that kind of encouragement. I think that's wonderful. Well, thank you so much, Sean, for being here today and walking us through a lot
thank
of
you
these
guys. It
concepts.
was very fun.
Yeah.
I
So,
enjoyed the conversation.
yeah, thank you to all of our listeners. Thank you for joining us here at SayoStudio. We'd love to hear comments, and please reshare with people and like if you like this. And we will see you next time. Bye.